This meeting is being recorded.
Critical,
This meeting is being
critical,
recorded.
critical transitions in complex systems, a seminar series or webinar series is going jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research, Germany. This webinar series brings together experts from fields such as ecology, climate science, neuroscience, fluid mechanics, etc., and aims to disseminate the state of the art in the prediction of critical transitions in these diverse fields of study. So the seminar typically takes place every month of the last Monday of the month. So mark your calendars. And before we introduce the speaker, a few housekeeping notes. I request everyone to turn off their microphones and kindly use the Q&A box in Zoom. It's at the bottom to ask the speaker your questions. We'll have ample time at the end to discuss questions and comments and so on. So with this, I invite Professor Jürgen Kurz, to introduce the speaker.
Yeah, thank you very much, Sujit. I'm really very happy to introduce our today's speaker. This is Professor Dr.Ludge. We have known for a long time. She has been and is very active in various fields of complex system science, nonlinear dynamics. She started very successfully in quantum dot semiconductor lasers from different viewpoints: time delay, synchronization, control, bifurcation, and very important and substantial papers. And also not only theoretically, what is difficult enough, but did also experiments, what I could not do. I'm really admire this. And but then she also went to other fields, more recently to reservoir computing, some kind of machine learning. And I found now a very recent paper on cognition and aging. I hope you will not estimate us then with aging, with our deficits in cognition. But only to mention, she is originally from Berlin, is really a Berliner. We have not so many Berliner. Studied there, then worked as a professor, had several stations at Technical University Berlin, and since a few years she has become a full professor at the Technical University Ilmenau. I think she will explain the area of Ilmenau. It's very nicely, but we are very happy to listen to your talk. Please, Kati.
Yeah, thank you very much, Jürgen, for this very nice introduction. I'm very happy to be part of the seminar series and talk about my research here today. So since it's this complex system seminar series, what I will be talking about today, this photonic reservoir computing, that is a nice application of nonlinear dynamics, and it shows nicely how the complex nonlinear response of physical systems can be used for computing. So that will be my topic today. And as you said, I will talk, well, shortly maybe about Ilmenau. I put this pinpoint here on the map of Germany. And Ilmenau is a small university in Germany, which has a focus on engineering and strong math and nonlinear dynamics focus also on in the past. And yeah, I moved there now more about 4 years ago. And some of the work I will present already from this time here in Ilmenau, and some will always also be from the time where I was still in Berlin. So the plan for today is to go through these 3 steps. I hope I will manage in time. So the last point, we will see if we go through all of that. But the first point, we will manage to first recap what delay induces in lasers when we look at the emission dynamics of these lasers. So these feedback-induced dynamics we will discuss and see how is that related to reservoir computing. And then we will talk about the time scales, how they matter for this computing concept. And the last point will then be how to optimize this computing. And before we start, so I could have named my talk how to compute with a laser, and that's what I asked Bing some years ago, so I don't know what comes out now. It was a picture that was created with Bing.com, and I asked him to show me a picture where a laser is transformed into a machine for artificial intelligence, and that's what he came up with. And I guess he was just looking too many James Bond videos. If you remember the first James Bond, where the laser was a tremendously dangerous weapon. And this picture is a bit similar. And we will see that in our case, the computing with a laser works a bit differently than what's shown here. Okay, so before we start, we have to talk a bit about lasers. And I also want to talk a bit about quantum dot lasers, because that's the laser that we will look at here in detail, because it has some nice properties to tune the timescales, and we want to look at the effect of the timescales on the reservoir computing. So the semiconductor quantum dot laser is a nice example. And what it is a semiconductor laser, a PN junction, with the difference, if you compare that to your computer mouse where you have a quantum well laser, we have these quantum dots, some localized structures that grow self-organized in an epitaxial process. This is a zoom of these dots. They have a size in the nanometer range. And for the electrons, that's like a zero-dimensional barrier, and they form localized states. So here's a band structure just for schematics. There are these localized wave functions, and that's where we get our inversion that we need for the laser process. So when we talk about lasing, I will talk about this transition between the laser quantum dot laser ground state. There's also an excited state in these quantum dot lasers, which is not important for this talk, but they could also emit light at these other wavelengths. And the most important point in these quantum dot lasers is how we get the electrons into these levels. So if we want to have a laser, we have to get the inversion, so more electrons in the upper than in the lower level. And in this quantum dot laser, that happens via Auger scattering. So we have an electrical current that brings the electrons into the carrier reservoir. And then somehow they need to get down. So they collide, and one goes down, and then the energy is given to another one that goes up. And this process fills the levels. And now for us as a dynamic person, it's just important how fast is this process, how probable is this process, and that can be calculated. Quantum mechanically, we get the overlap integrals, and at the end it all boils down to a scattering rate, and we can write down rate equations for the laser, which I have done here in this lower right part. 3 equations for the carriers in the reservoir. That's where we pump. So we have the pump current here, electrons come in. Then we have an equation also for the time change of the electrons in the localized levels. And here is this Auger scattering process that I just introduced. So it's this scattering rate. And we have to remember that one because we will tune that later on. So this is where it appears in the equations. That's our scattering rate R. It fills the quantum dot levels. And then, of course, when they enter here, they have to leave the other reservoirs. So here, the same term with a minus. And then I said it's a laser, so we have these other 2 important contributions, which is the nonlinear light matter interaction. So the inversion is built in the quantum dot levels and then proportional to the intensity of the electric field, which is the electric field squared. This is basically what we need as a dynamic equation for later on. I mean, who is interested more in quantum dot lasers and the microscopic modeling, there is a book that I edited. There is more details about the scattering processes. For us, it all comes down to the scattering rate R. Okay, so what does this R do to our laser? If you are familiar with laser dynamics, what happens? So let's first focus here on the lower right. If you turn a laser on, it needs some time to build up the inversion, and then it needs some time to find the steady state value. So it overshoots, it undershoots, and then we have this relaxation oscillations to a steady state. And how fast this steady state is reached and how fast these oscillations on the way are, that is described by relaxation oscillation parameters, and that's the figure here. When we fit these turn-on dynamics, we get a frequency and we get a damping of this turn-on process. So I will call that the relaxation oscillation frequency and turn-on damping. And these two parameters, they change over all the different lasers that exist. So if you have a gas laser, a CO2 laser, you have strong oscillations, then there are solid state lasers where you don't have these, the damping is much stronger. But for these semiconductor laser, usually we have a dependence like seen here on the right, where you have strong relaxation oscillations. But if we take a quantum dot laser, and now here is this important scattering rate R. So we change a bit the size of the quantum dots, which makes the scattering faster or slower. And then we move around this x-axis. And then we see what's happening with our turn-on dynamics. And what we see, it's a very nonlinear behavior. On both ends, we have a frequency that's much higher than the damping. And that leads to very strong relaxation oscillations. So these very strong spiking-like behavior is for very small scattering rates in pink, and also for very high scattering rates in green. And in the middle, where all these different carrier types in the reservoir and in the dot relax on a similar time scale, the dynamics that we see in the light turn-on curve is overdamped. So if you look at it this way, it looks a bit more boring than the other two cases. But from the dynamical side, it's less boring because we have 3 dynamic degrees of freedom. So if you plot the whole phase space, it's more rich in the middle than on the other sides, because there we can reduce the equations to 2. So we keep that in mind. We have this tuning parameter, and we can change the number of degrees of freedom and these turn-on dynamics with this scattering rate. Okay, so to get it to compute, I already spoiled in the beginning, we need some feedback. So we also need to recap what this feedback does to the laser dynamics. So here is now just the equation for the field. The carrier equations we still have, just not written here. And we add to the field equation this delayed feedback term, which comes from a mirror that we put behind our laser. And then the light comes back with a certain strength, that is this K parameter here, the feedback strength, and with a certain phase difference to the phase when it was coupled out. And this is this feedback term. And then that is already also known for a long time, this feedback induces very complex responses of our laser. And I plotted that here in the parameter space of the feedback phase and strength. So these 2 parameters here. And what we see in color are the number of maxima we found in the response. So imagine we have this laser, we put the mirror behind, and it starts blinking, like sometimes it's on, sometimes it's off. So that is the intensity over time. And then we collect all these maxima and we color code the number of different maxima that we found. So here we find a lot of them, that's red. If it's more regular oscillations, we only have 2 different maxima. So it's this level and the other level. And the most simple oscillations we could get is just 1 maximum. Then it's like a sinusoidal oscillation, which we found here in the bright yellow region. And from the bifurcation side, we can characterize these transitions. So the first thing that's obvious is it's changing from constant intensity lasing, that's the blue part, to these oscillations in yellow. And to see that more clear what's going on, we make a line scan here along this line. And we see that is first the constant wave intensity. And then we have this square root-like increase of the extrema that we found, which is characteristic of a Hopf bifurcation. So here we have a delay-induced Hopf bifurcation. And then we see something else that's very typical for delay systems, that is multi-stability, because when we sweep up, so we tune our initial conditions always slightly from one step to the next. We follow the red curve, no, the blue curve. And when we sweep down, we follow the red curve. And we see here in the middle, I can have two different responses of my laser. It can be either dynamics with a lot of maxima, so very chaotic emission, or it can also be stable. So we have multi-stability that is induced by this delayed feedback. And in between these complex regions, so always when we have these many points, the emission is complex. That's the red one here on the left. It comes again here. In between those points, we have steady state emission. And this steady state emission is described by external cavity modes. Since we have light intensity, which is given by the electric field squared, we still have this phase or the frequency of our emission as a possible parameter. So we still have time dependence because the light is, the electric field is oscillating on the circle, but the intensity is constant. These are our regions of constant emission. So this is the rough pattern. We need to know what's happening when we put delay. And something else that's important, when the delay becomes larger, the number of solution increases. So this is plotted here. That was the old picture. We've seen that one. If we go down now, we get much more of these constant wave emissions with different intensity, which are new stable emission solutions. You can think of it of more standing waves with more maxima inside these external cavities. So the longer the delay, the more solutions we can have, and the more or the higher the degree of multi-stability is. So we also keep that in mind. Higher delay means higher degree of multi-stability. And specifically for this quantum dot laser, already small delay is also interesting. I'm just showing this short example here. That's also the same quantum dot laser, short delay time. This is this first bifurcation cascade. And what's plotted here in blue is now this frequency, the color of the emitted light. And we see this is the first external cavity mode. The second one is born in a saddle node bifurcation, which happens here at this bifurcation point, one stable and one unstable mode. The stable one we see here then as this constant wave emission. But at this transition where this chaotic attractor has a crisis, we can observe very broadband chaotic emission of this laser. And that is plotted here. So for parameter value, just shortly before it becomes stable again, this quantum dot laser was a bit different than the one before because this one can emit at the other wavelengths too. We see these pulses with very complex shapes. So it comes like bursting, and then this excited state turns on and turns off again. And the power spectrum is very broad. So in case someone needs a chaotic signal, quantum dot lasers are also good candidates to get to produce that. And broadband chaos generation is not the topic of my talk today. Instead, I wanted to look at when we can use these lasers for computing applications, for the reservoir computing. So that's why I show you again this plot of the feedback phase and the feedback strength with the different sweep directions, upsweep, downsweep. So now all of the features in here we have already seen. So this is the subtle node bifurcation where this new solution is born. There's also a subtle node bifurcation. So it's like you fold the sheet of paper and these solutions are lying on top of each other. And this upper solution here then undergoes half bifurcation. The lower solution does not. So depending on the sweep direction, we land on the one or the other solution. And if we don't sweep, if we choose constant initial conditions for integrating our delay differential equation, then we always hop onto the solution that is closest to the initial conditions. So that is then either the first half here and the lower part of this other one. These saddle node bifurcations are also known analytically. I wrote on the equation here, it's not that crucial, but it might be interesting how these saddle node bifurcations change with the laser parameter. And for those, these carrier lifetimes and our scattering rates don't make an impact. So they stay put even when we tune the scattering rates, while this Hopf bifurcation will change depending on the damping of the relaxation oscillations that we talked about earlier. And as a little spoiler now, this color code shows you how good the laser is in predicting the future of certain time series. Details will come in a second. It is good for this low feedback strength. It's not working good in this complex region. And obviously, the dynamics behind this laser emission is also an issue for the performance. And of course, now I have to explain you what this color code here is. So somehow we convinced the laser to do this prediction, to do computing. And for that, of course, we somehow had to inject information into the laser, which can be done on different ways. We can either optically inject light, that would be adding a term to the electric field equation. And then we also have two possibilities: tuning the injection strength or tuning the phase. So both is possible. And we could also inject the data via the pump current. That will be electrical injection. Since we have the carriers, we can electrically address the laser, and that will be electrical carrier injection. So we can inject data. And now we still have the question, how is it computing? Where's the neural network? So everyone usually talks about neural networks, and now we just have one laser. And for that, we have to, or I have to introduce this concept of reservoir computing, which is basically a very shallow deep neural network. Since it's not deep, it's just one layer, and you only train the final layer. And everything before is your dynamical system. So the reservoir is the dynamical system. You put in data and you read out the response, which is then trained. So you don't touch the reservoir. You don't do these deep network training where you adjust your reservoir. You take the reservoir as it is and you read out. And what I plotted here on the left, this time multiplex reservoir computing, the difference to neural networks is I don't have a network in space, but more in time. And that's why I had here this analogy of the spatially multiplexed reservoirs, which you might have heard before. You have an echo state network randomly connected. You address some nodes with your input and you read out some nodes with your output and train the weights. And now with the time multiplexed, we do the same, just in time. So our input is coming in time, one input every clock cycle, and then we read it out in time. And now the point is, if we would just inject one input data in time, if we compare that to that spatially multiplexed version, that would be like injecting all the same information into all the nodes, which is not a very high dimensional input then. And to mitigate that problem, this concept of the mask has been introduced. That was already in 2011 by Appeltant. And they said if I do this time multiplexing, I multiply a mask on top of my input. So I have a diverse response, a transient response in time. I send that on to my reservoir, and then I read out in time at my different positions where I had the different mask steps. So that's basically all we need. And then we just have to decide which reservoir. And in my case, this will be the quantum dot laser with the feedback. So for the training, how that is done, let's look at it again in a zoom of this training process. So we have the readout, we have the detector. This laser is reacting to the input, to the masked input. And then the detector detects some time evolution, and I read out the different intensities in time. So if this is one clock cycle, one input data, this will be one row of my state matrix S. And in case I already had the weights, then I could just multiply the weights with the state matrix, which gives me an output. That's all what the computing part is about. If I have weights, I multiply them, I have an output. I just need the weights, and that is the training part. And to do the training, I, of course, need to have some kind of task, which I didn't talk about yet. But let's say we have some kind of target where I want to have my output, and then I compare that to the output my laser gives me at the moment. And then I need to solve this minimization problem. So how to choose the weights to minimize the distance between target and output, which is a minimization problem that you might all know when you try to fit a linear curve to a cloud of data. And that's this linear regression problem, which Gauss and Legendre already figured out 200 years ago. So this minimization problem can be solved analytically, and the solution is plotted here. This minimizes the distance written above, and all I need is the state matrix, which contains all the different responses of my laser, can be determined experimentally. That is a regularization parameter that avoids overfitting. And then I need the target. So if I know what to do with my laser, I can analytically get the weights by just inverting this matrix here. And the network size is given by the number of points that I measure during one clock cycle. So I put in one data point, I have the mask on top, and then outside I sample, and if I sample 100 times in this clock cycle, my network has a size of 100. What's plotted here, I just sampled 5 times, so here my network would just be a network of 5 different nodes, and these are these virtual nodes that we will talk about also later. So how often I sample in the clock cycle, that is my network dimension. And you can already see if it's 100 points here, it might take longer. So my clock cycle might need to be larger. So the time, or how fast this system can process information, is also related to how long my clock cycle needs to be. Okay, and the last thing we need to get us started is the task. Of course, you can think of various tasks like trying to predict the weather, or looking at a machine that starts to become unstable and you want to predict when that happens. Here, I focus on some toy tasks, which is the Lorentz 63. I mean, it comes from the weather. It is this 3-dimensional system that has a chaotic attractor, a time series that looks like this here for the right choice of parameters of these C1, C2, and C3. And our task would be, if I give my laser the X, can it predict, for instance, the Z one time step into the future? Another task could also be to predict the X one time step into the future. So that will be one toy task. And the other one is the Mackie glass task that I will talk about. That's originating from a delay differential equation derived from some blood flow models. For us, it's important. It's a dynamical system with delay. So if we look at the dynamics, if we want to predict this dynamics, we might need a lot of history to predict this long time and the short-term oscillations. So this is a task which is with high memory requirements. And the input would be X, and predicting would be then 1 or 2 or 12 steps ahead. These will be all different possible tasks. And good and bad is then, good and bad performance of the laser will be measured by the normalized root mean square error. So there, it's just a metric measure where we determine the distance between target and output, normalized to the variance of the target. And with that, we come back to the picture you've already seen before, this teaser picture that was the one here on the left. And if we now go from the left to the right, we again tune our scattering rates of the quantum dot laser. We have this small little pictures on the top row. So we tune the laser from oscillating to strongly damped to oscillating again. The top row here is the dynamics, so the maxima that we find in the emission or steady state dynamics, then it's blue. And what we see, as we've already seen here on the left, the good performance is related to the bifurcation structure, but in that case, not that strongly, because the best performance is always found here at these red points, and they are always more or less at these small feedback strengths. And if we just have a small feedback strength, it's performing nicely. And if we compare the absolute values, that's these normalized root mean square error as a function of the scattering rate, which is now orange. It was green before. So it is this rate, how fast the electrons enter the quantum dots. And that was surprising for us. The best error, so that is here, this point here, always where the red point is, the best errors can be reached for very high or very small scattering rates. While in the middle, where we have more degrees of freedom, because we have the carriers in the quantum dot and the reservoir that we cannot eliminate, still there it's not performing the best. So that was the first surprising for us, because we thought we take the quantum dot laser, we have more degrees of freedom, it should compute better. But the problem is you also need to sample the higher degrees of freedom. And if we just sample in the intensity, we just get the boring response, and the complex response and the carriers we don't see. And the other important thing to notice is that was for these Lorentz tasks. So it was Lorentz one step ahead prediction, X to X. If we change to the Mackey-Glass task, more or less the same picture, the dynamics didn't change. That is the computing performance. And what changed is where the good performance regions are. So these red stars now all moved to the right, because for this Mackey-Glass task, that was this delay differential equation with this long and short-term oscillations, there the best performing regions are always close to the Hopf bifurcation. So for the Mackey-Glass task, we see a much higher correlation between the dynamics in the bifurcation structure and the regions of good performance. So it's here for the very high scattering rates, we see the best performance is found right at the Hopf bifurcation. In this reservoir computing business, this is known as good performance at the edge of chaos, which we, however, have to note that this is task dependent. So for the Lorentz task that we had seen before, that wasn't true, because that task didn't need so much memory, but the Mackey-Glass task needs memory. And the closer we come to the Hopf, the more the response of the laser is undamped. So close to the Hopf, we have very long transients, and these very long transients help us to get memory into the system. Okay, so we need to remember reservoir computing can be done with a laser if we use this time multiplex scheme. But it seems to be very task dependent and very dynamics dependent. And that's why we want to look at this second point here. What happens if we deliberately change these timescales? And that I want to focus on now. So this one parameter I didn't talk about much until now, and that is this theta, which is the temporal distance between two virtual nodes. So this is the mask here, and the length of one mask step. The t is one input data, and this theta is one mask step. And from the nonlinear system theory, you can already imagine if it's much smaller than your characteristic time scale, the system is not responding. And if it's much longer, then the system is always in a steady state. So having too small or too large theta, here it's plotted as a function of theta, too small, too large, the performance won't be good. So we have to adjust this time scale to the system response time, which has been already known since 2011. But the question that we ask ourselves is, what does matching mean in this case? So we can tune the theta, and then we find there's an optimal theta we also see that there are resonances when the delay time equals the clock cycle, which gives us bad performance. We'll talk about that in a second, but we get this optimal performance. And obviously this optimal performance theta, so this time scale, if we go back to our scattering rates, here are the scattering rates. And I showed you in the beginning that this quantum dot laser can have these different turn-on dynamics. And obviously, for these different turn-on dynamics, we also get very different optimal theta values. So in the overdamped region, we can inject the information much faster. We have a much lower theta, while for these good performing regions with these high scattering rates, we got a better performance, but it also takes such much longer to do the computation because we have to wait longer for the system to react. And that is one thing, depending on the system, this injection can be faster or slower. But the other thing is the whole experiment here was done with a constant delay time. So this mirror was behind the laser, wasn't moving. And then we started changing the delay time. And then also these optimal theta values changed. And that is plotted here. So this color code going from bottom to the top is now different delay times. And from left to the right, that is the clock cycle or the virtual node distance. That was the 1D scan we just saw. And black or dark blue is again very good performance. And interestingly, the very good performance values lie along one linear scan here, which gives us a certain ratio between the tau and the clock cycle. And this ratio also again changes with our scattering rate. This is a higher R, and here obviously we need longer, or the T has to be 1.4, the clock cycle. So then we plotted the slope of this white line here as a function of the scattering rates again. And we saw that this also follows the damping of our turn-on dynamics. So for this very strongly damped case, we needed a higher clock cycle. And then we ask ourselves why and how is that related to this internal coupling topology. And for that, we now have to switch into this network picture. I mean, we have this time multiplexed reservoir computer, which means every point in time reacts with its neighbor in the past, and it can somehow change the reaction of the future. Let's say the carrier are still depleted, then the next input data will also change. So this circle here are the virtual nodes that are coupled in this circle-like topology, and the light arrows are this coupling due to the inertia of our relaxation oscillations, and the dark arrows are the coupling due to the delay. So if our delay is equal to the clock cycle, that means every point in time always gets the information about its past back. So we have the self-coupling of every virtual node. And that would be this orange line here, if tau equals our clock cycle, which is not the optimal position as we see. That is what we found numerically for the optimal position. And what's now changing from the topology point of view is when we have unequal delay and clock cycle, it means that one virtual node gets the information added from a node in the past or in the future, depending on if it's larger or smaller. And these thick arrows change to a different coupling topology. And that is the reason why an unequal tau and t lead to a more complex coupling topology, which can be beneficial, as we see here, that in that case we get better performance. And we can write that also down. So our tau is then the clock cycle plus a number of virtual nodes. And if we divide that by t, we get that the slope is varying between slightly around 1, that is this dashed line here. And then depending on which memory is needed, we can tune the n and get the optimal slope, which is again task dependent. So that is similar to the arguments I talked about before, because if we look at the Mackey-Glass task now, so here's the Mackey-Glass task, that's the Lorentz X task, plotted is the slope as a function of the scattering rate. And the important thing to look at is here that for the Mackey-Glass 2-step ahead prediction, we need a slope around 2. So this desynchronized regime, there our tau needs to be an integer multiple of the clock cycle plus some virtual nodes, because then we can give it the memory it needs to remember enough past input points to predict the future. So this slope or this tuning of the delay can be used to give the system additional memory that we don't have from this next neighbor coupling, from the relaxation oscillations. We have additional tuning parameter, which is the delay, to give it more memory. And in the limiting case, when we don't have these errors, so where we have a system that is reacting instantaneously, that is the case of a nonlinear map. So this is this dynamical system here, can be a semiconductor optical amplifier that's just amplifying with a nonlinearity. That's written here, that's this G, and it is reacting. It's always adding the dynamics with a delay tau. And in that case, we don't have these light errors from the dynamics. We just have the coupling from the delay. And if this is just by 1 theta off, we have a ring coupling. If it's equal, we have uncoupled nodes. And here we have a scan of the delay, so a continuous scan of the delay time. And we see that also there we find an optimum value. For this case, it was the Lorentz cross prediction. So if I want to predict one step in Z, when I gave it the X value with this discretization step, and if we zoom into this optimal region, we find that we need to be away from the resonances, because at the resonances we have uncoupled nodes. And in that case, for this Lorentz cross prediction, the ratio of 8 is optimal for the best performance. So we not only have the dynamics to tune the properties of our reservoir, but also the delay to adjust that to the memory requirements, which is a nice thing because the delay sometimes you can tune from the outside. So if the laser has to change its task from one prediction to the next, it can be slightly tuned by this delay time. So now one other thing that you could ask, well, if I can characterize the memory properties of the laser, like this linear memory capacity here that can be computed, that's a task where you give it some input data and then you ask, hey, can you remember the last inputs? And then you can compute this memory capacity, so how many past inputs I can remember. And then it would be nice to predict good regions for certain tasks. So if we try that, this is the memory capacity. So these are now 2 lasers that are coupled with 2 delays. These are the 2 axes. And obviously, when the delay is small, it has no memory. When the delay is large, it has more memory. And for predicting, that was the number 10 time series here, there are obviously some sweet spots. Blue is good. But now if we take other tasks, Lorentz and Mackey-Glass, they all look different. So as you have seen before, different tasks need different properties of the laser. And that is something which makes it hard. Even if I know the memory properties of my reservoir, if I can nicely characterize my reservoir, I still don't know what is a good point, because with something that can be good for NAMA can be very bad for Lorentz. Lorentz doesn't need much memory here, but the Mackey-Glass needs more memory. So we were asking ourselves, can we maybe predict a good operation region from the memory properties? And is there a way to derive analytically the regions of good performance? Or put it in another way, can I characterize my task beforehand to know what it needs? And that's what we tried here, which actually worked. So when you decompose your target, which is the Lorentz time series, into Legendre, into a series of Legendre polynomials. So let's say we take the Lorentz and we make the series expansion, we get some coefficients for the different Legendre polynomials. And then it can be shown that the different memory properties that I need from my system correspond to these series expansion coefficients that I have in my task. So I can predict the error from these expansion coefficients. That is my series expansion. And these CNs are the nonlinear memory capacities of my reservoir, my laser system. And if we plot this predicted error, which is not computed, so I didn't use the linear regression. I just used the memory properties. So I trained it to memorize stuff. And if I compare that, it seems to work very nicely. So the first line here is the calculated error after training with the linear regression. And this is the predicted error from the memory capacity. And we see for some tasks, the method works very nicely. For the number 10, for instance, because there we really have uncorrelated input. For the Lorentz, it still kind of works. For the Mackie glass, we have some problem because there the input is very highly correlated. And then the analytics breaks down because purely mathematically speaking, it's just true, or just can be proven that this is true for uncorrelated input. But still, it gives you a feeling for the properties of your task. Okay, so as I expected, I'm a bit short on time on this last point, but shortly, I want to show you some more ways how to optimize such an optical laser reservoir computer. And that can be done by optical injection. So we now make a rollback to the dynamical analysis of a system. And in this time, it is the laser with optical injection. So if I want to inject optically, I need to shine with another laser with a certain frequency and a certain intensity. And then I can characterize the dynamics in this parameter space again. I have a nice bifurcation structure. I have Hopf bifurcations here, subtle node bifurcations, which I can see by looking at the oscillation periods of the dynamics. So here we have very high periods close to the bifurcation point, which is a sign for a subtle node bifurcation. While here the period starts with a constant value, a sign for Hopf bifurcation. And here the period doubles. So this is a period doubling bifurcation. And having understood this, so injecting a laser with a certain frequency is like forcing an oscillator with a different frequency. So it's like a pendulum driven with a different frequency. We have this resonance tongue. We can now look at this reservoir computing again. So we have the data that comes in optically, and we still put a laser mirror behind. So now combined the injection, which gives us the locking cone, and the mirror, which gives us the different external cavity modes that I talked about in the beginning. The longer the delay, the more external cavity modes I have. And what's happening with this locking cone is very interesting because it can now lock to all these external cavity modes that exist in this multi-stable system. So for the small delay, not much changes, but if it gets a bit larger, we get additional noses here. And for even higher delay, it logs to all these different external cavity modes. So the distance between two noses is always 1 over the delay time. I have this oscillation between the different intensities of the different external cavity modes. So keeping that in mind, that I have a complex locking region, I can now look whether the computing performance works better or not with this optical injection. And that had been done here. That was a spin VCSEL, a system with 2 modes, but still what we see, now the color code changed, but good is dark blue. Very good performance is found close to the edge of this locking tongue, and we see all these different teeth, the different teeth, and one tooth is the locking to one of these external cavity modes. And I skipped this one here, but I wanted to show this at the end because that comes back now to our quantum dot laser, where we tuned the quantum dot laser scattering rate again from left to right, not damped, over damped, and normal quantum like turn and dynamics. And then we see the dynamics in the upper part and the performance in the lower part. So blue here means constant wave emission, and that also shows us this dark blue very good performance region. And compared to the case that I showed you before with just the feedback, we can improve the performance by about 30, 45, or 40%. So this additional optical injection allows us to improve the performance even further because the response of our system becomes more rich. So we have an additional tuning parameter if we use lasers because we can drive them externally with another laser. Okay, looking at the time, I think I will just shortly mention that wasn't everything that can be done to give the system additional memory. Because what I talked about was just this middle part. I have a nonlinearity, I have feedback, I can tune the time scales. So I showed you tuning time scales with this Turner dynamics, tuning the delay, tuning with the injections, so that all came down to this middle part. But what we can also do is leave the reservoir like it is and give the system additional memory just via the input or via the output, which is a very experimentally easy procedure because the input delay is just a pre-processing. I need to do something with the data before it goes into the reservoir. And also the output delay is something very easy because I just need to do something with my readout before I do the linear regression. And surprisingly, that also works very nice when you have a nonlinear system which is lacking memory. You can give it the memory via this output and input delay. So this is a example for the post-processing. If I give it the delay by just concatenating the state matrix. So this S here is the different rows of my state matrix where I read out the laser intensity. And now imagine I read that out and I just keep the results for a while and concatenate that with a readout at some later time. So I have this time shift D2 and the time shift D2 and D3. So just a post-processing of putting the same columns again, just from the past. And then I see here in this color code, which is the performance as a function of this time shift in the readout. So nothing changed with the reservoir, that I can optimize my performance a lot. So I can give it additional memory, which the system didn't have because I couldn't tune maybe that nicely my internal coupling topology. Then I still have the possibility to tune, to decouple the memory from the system's dynamics by doing this post-processing. And if I compare all the three methods, and it's the input delays, this panel, the second one, the output delay is the third panel, and the feedback delay, what we talked about with this quantum dot laser, is the last panel. Some system parameters, it's the feedback strength and input scaling. But what you should look at is, if we don't tune, we have a strong dependence on hyperparameters. While when we add the timescales that our system needs, which will be different for every task, that's what we learned in the other part of the talk. So if I give the system the timescales that the task needs, either in the input or in the output or with the feedback itself, then I can reduce the error in my prediction performance a lot. And it doesn't really matter where I include this additional delay. It just matters that I include the right timescale. And with that, I want to finish my talk. So I hope I convinced you that reservoir computing with quantum dot lasers and optical feedback is a nice setup for an optical reservoir computer, and I can tune the performance with changing scattering rates. Then we talked about these injection timescales, which are very important in this time multiplex scheme, because all we do is we use transient dynamics, so we have to adjust to the system timescale. And we shortly looked at the injection, which shows very complex bifurcation scenarios. And we looked at ways to include memory externally decoupled from the dynamics of the system. And of course, I have to thank all my cooperators. And this is the group in Ilmenau. And here, that is a picture from the group still in Berlin. And I also want to thank the funding, which was some former work was funded by the DFG in the framework of the SFB 910. And the newer work happens also in the framework of an EU Spike Pro Horizon Pathfinder project. Okay, so with that, I want to thank you for your attention.
Yeah, thank you very much, Kati, for this very interesting talk. And I hand over to Sujit to manage the Q&A things, please.
Yeah, thank you, Jürgen. There are 2 questions in the Q&A box already, so perhaps you could stop the presentation mode and see it.
Yes, I will stop the presentation. Wait. And
2 questions by Singh.
And then I can have a look. Oh yeah, one question is related to the laser equations that I showed, mentioning that it was linear dependent variables. The point here was that the stimulated emission is a product of the carrier occupation number and the intensity. So a product of 2 dynamic variables is then not a linear equation anymore. That's where the nonlinearity lies in the laser. And the second question asks if it's equivalent to an optical network. Is it interesting to think how the number of layers in neurons are defined and chosen in such a neural network over time instead of space, and how the weights are updated through backpropagation? Is it equivalent to the conventional neural network we use? No, it is not equivalent, but there have been studies you can try to mimic a deep neural network with a system of multiple delay lines. So you can map a neural network with a certain topology with a time multiplexed reservoir computing system with multiple delay lines, but it's not an easy one-to-one mapping. So in my case, where I just had this one delay, then of course it's not a layer with multiple, not a network with multiple layers. It is more ring network-like, a bit more complex due to the internal dynamics. I hope that answers it. That's a complicated way of doing the FNA because you don't get a feedback whether that answered the question. Okay, I keep on reading. There is another question, and that is there a motivation for using a decomposition using Legendre polynomials? Well, yes, the motivation was that we wanted to map that to the memory, nonlinear memory capacities, and those nonlinear memory capacities were also series, or you characterize the linear memory by how well certain Legendre polynomials of the inputs are recalled. So it was more adjusting the basis to the basis that was used for the memory capacity. That's basically all of a motivation. Of course, you can use different series expansion, but then the mathematical mapping to the memory capacity becomes more complex. So then there's another question. Does delay require optimization and has certain limits? Is it possible for the delay? Oops, now it's moving. Is it possible for the delay to completely overlap at zero phase, thereby rendering the delay meaningless? Well, it is, I wouldn't say it's then meaningless. If you have zero phase and a perfect match of the delay and the clock cycle, then you have all self-coupled virtual nodes, which is then still meaningful in terms of memory. So the system then still has memory since you have the light in the external cavity coming back and getting overlaid. So it won't induce additional dynamics then, but still you will have the memory. Okay. Why do you particularly consider an overdamped dynamics? Yes, that's also a good question. And that was related to the physics of the lasers that existed. So when these quantum dot lasers grow self-organized, we had some corporations back then with the Wimber group in Berlin, and these lasers showed this very overdamped dynamics. So the physically existing quantum dot lasers were strongly overdamped, and that is due to these different interactions of the different carrier types and the complex scattering processes. And that was why we specifically looked at them too, because they existed in reality. Nowadays, they can also grow these quantum dot lasers on silicon, and there it's not always overdamped dynamics that they show. So it's always depending on the material system. So another question. So is it possible to predict phase space? I think I didn't really understand. I don't really understand this question. So we are always coming from this rate equation modeling, and there, of course, we can plot the dynamics in phase space. So from the modeling side, we can predict how the data that we inject is transformed in phase space. What we can't do is to derive a certain nonlinearity that would be analog to these neural networks where you have, like say, the tangents, hyperbolic tangent nonlinearity, and then you know how this transformation is. That is more complex in the time-dependent systems because you have the transient response, you have always a state-dependent response. But it can be predicted as long as we know the governing equations of the dynamics. So one last question I read here. Can we use such optical reservoir computing-based neural networks to predict and study optical soliton dynamics in laser cavity for dissipative soliton as it is studied using conventional neural networks like PIN? What is a PIN? I think optical reservoir computing should be more efficient in this. That should be possible. The question is always how to input the data and how much or how high dimensional response you need. I personally didn't do that, but it can be done, I would say. If it's better than the neural networks, I'm not sure, depending on how much recurrencies you have in there. So what you definitely need is memory.
Okay, that comes to the end of the questions. If you
physics informed neural networks. Now I got the PIN translation. Okay.
If any of the panelists want to say something or ask a question.
Yeah.
Yeah,
Can
Professor
I start?
Ambika. Yeah.
Yes, I have a couple of questions. One is, in the task that you discussed, you were mentioning about predicting one step ahead. So suppose we have to predict 10 steps ahead or 100 steps ahead. Do you do it sequentially?
You have different options. So if you definitely know that you only want to know 100 steps ahead, then the best performing version would be to train 100 steps ahead already.
Oh, I see.
Because
Okay.
when you train one step ahead and you do that iteratively, then you have a lot of errors that pile up, right? Another version is that you really build a surrogate where you have these autonomously working systems so that they always get fed with their own output. So you have a loop at the end. And then the idea is that they run infinitively and give the right dynamics, which is, of course, also not that easy because these higher dimensional systems, they tend to be stable.
One more thing is the two examples you mentioned, the Lorentz system and the Mackay glass system. The Mackay glass has inherent time delay in it. So it can have hyperchaos also, not chaotic behavior alone. So does it affect the computing part? For example, a chaotic time series or it's a hyperchaotic time series, how does it affect you need more memory there or how does it turn out?
Oh, that's a good question. I didn't look at that, but it will definitely change the memory requirements. If it's more or less, you would need to have a look at the specific time scale. But when I talked about this Mackay glass task, it was more this specific parameter choice. So as soon as you tune the parameters, if you have a different attractor, then the requirements will change.
Yeah.
Yeah.
Okay. Thank you. Very nice talk.
Thank you.
Yeah, looks like there are no more questions. So let's thank the speaker for this wonderful talk. Thank you very much for coming. And the next seminar will be from Professor Ambika. It will be on April 28th. It's a Monday again. On the topic is emergent dynamics and transitions on multiplex networks. Same time as today. A very interesting talk. Please mark it on your calendar. See you 1 month later. Thank you all. Have
Thank
a
you
good
very
day.
much.
Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye.